Okay, welcome everyone to this first afternoon session. I will talk about the Java modeling language, which is a specification language which I will introduce here, and it is used as a basis for both static and dynamic verification, including runtime verification of a certain kind. I'm Wolfgang Ahrendt. I work at Chalmers University in Sweden, and I'm very happy to be here and to present something to you here. So first, before I start with talking about JML, I want to give a little bit of a bigger picture. Maybe this is also something which we can discuss here and also later. I'm trying to kind of categorize the different methods and approaches to specification, to properties, to verification. And I categorize them here into trace-focused and data-focused things. We have here the dimensions runtime verification, static verification, properties, specification. Runtime verification, when we can focus on different things in runtime verification. And many of the things which you will hear about in this school here, and which you will hear about or read about when you open the proceedings of a runtime verification conference, are something which I call now here runtime trace checking, where the focus is properties of particular traces, which are, certain traces are allowed, other traces are not allowed, and so on. Runtime assertion checking is something different, which has a kind of different focus. A related technique, if you look at the specification methodologies and about the semantics of the property languages, then on the static verification side, what comes closest to runtime trace checking is model checking, which has been mentioned earlier today, and on the something which comes closer to runtime assertion checking is deductive verification. So these are now verification, static and dynamic verification methodologies. But what are the properties all about? Here the properties focus on valid traces. What is valid, what is not valid in terms of traces. And the languages say something about that. Down here we specify valid data in specific points, specific code locations. So there's a strong connection to the source code here, and you say, okay, at this point the data should have certain property, and at that point should have another property, or if it has that property at this point, then it has that property at another point, and so on. But what you say, what you talk about is the data. Specification side, so here you have some formalisms, you have temporal logics, you have automata, regular languages, there are also other things. Down here, things are based on first order logic. To talk about the data in terms of first order logic, and there are assertion languages here which build on top of first order. But then the whole picture is more complicated, and there are, here in this world people try to say more and more about data and incorporate data, and then you do slicing according to certain data and so on. Down here people also see acknowledge the need to talk about traces sometimes, and then you try to code them into your data somehow here. And also here you have all kinds of extensions on both sides. But this is a kind of a rough mental model, which I use as a starting point, which I'm also happy to discuss with you and with colleagues and so on. Okay. The talk of today is all about this row here, the Java modeling language. It's used for runtime assertion checking. It's used for deductive verification. We talk about valid data and specific code locations based on first order and extensions of that. So my lecture will be the Java modeling language. I introduce the language, and that is most of my lecture. Then I will talk about static verification of JML and about runtime assertion checking of JML, both the static and the dynamic side. But these things will not be, neither of them will be really extensive. Okay, and when it comes to literature, I wrote with three other people recently overview of JML and a tutorial for JML formal specification with the Java modeling language. It's part of the key book, which is a book about about a static verification system, which I will say something about later. And that is a kind of state-of-the-art verification system for Java, and it uses JML as a front end. So a lot in this book is not so relevant for this lecture here now, but this is here you find what I'm talking about, and you find much more. Okay, the language. So the language is kind of unit, code unit oriented. So we talk about code units, and in the object-oriented setting, these units are interfaces, classes, and methods. We start now here with method specifications, and we look at the other things later. So method specifications, they can talk about initial values of formal parameters. They can talk about the result value. They can talk about pre-state, post-state. And when they do that, we stress the different roles, the obligation, the responsibilities in the specification. And this overall methodology is referred to as design by contract, which was popularized by Bertrand Meyer. And he has built this into the language Eiffel. So the specification can be viewed as a contract of some kind between the caller and the callee, and the caller guarantees a certain outcome. So the code you're specifying has to guarantee some outcome which is specified, but you also specify assumptions you make on your caller, right? So the implementer cannot guarantee everything, but it can guarantee certain he or she can guarantee certain things, assuming other things which the callee takes care of. We will see examples of that. Okay, here's the first, now this is not yet JML, but this is a running example I used in the first bit of my lecture. This is Java code. We have a class, a teller machine. This is where you get money from a machine. We have fields, inserted card, wrong pin counter, custom authenticated. This is a reference to a different object, and these are kind of internal, they are of primitive type. Inserted card is initially null. So they have some initial values, but they are not important now. We have certain methods here: insert card, enter pin, account balance, withdraw. I will only look at enter pin now in my example. So it takes pin as an input. And the informal specification of enter pin looks like this here. This is natural language. Enter the pin that belongs to the currently inserted bank card into the ATM. If a wrong pin is entered 3 times in a row, the card is confiscated. After having entered the correct pin, the customer is regarded as authenticated. So this is some English prosa about what this could mean. We try to structure this now a bit to come closer to formal specification. Because this is totally unstructured here, it says something about something. Here I try to make a start by structuring things into what is guaranteed by this implementation, what is assumed by this implementation. So there are certain preconditions, certain postconditions, and they are always paired. A precondition one precondition could, for instance, say, let's assume the card is inserted, the user is not yet authenticated, and the PIN I get is correct. Then, in that case, the implementer has to authenticate the user. Under another assumption where everything is the same, but the PIN is not correct, but the wrong PIN counter is small enough, then the wrong PIN counter should be increased by 1, and the user is not authenticated. And in a similar scenario where the PIN is not correct, but the wrong PIN counter has exceeded its limit, then the card is confiscated, whatever that means formally. We will see about that. And the user is not authenticated. So this already gives a lot more structure than this. It's still English, but it's a lot more structure than the text I just had. Okay. So we have these pre-post condition pairs which play an important role in JML, and the intuitive meaning is when M is called in any state satisfying the precondition, then in any terminating state of M, the post condition is true. Right? And you interrupt me if you have any questions. Good. So no guarantees are given if the precondition is not satisfied. The implementer doesn't have can do what he or she wants in those cases. Termination may or may not be guaranteed. We can be more precise when it comes to termination, but I'll come to that later. And in case of termination, the termination may be normal or abrupt. And we don't talk about these things just now here, but they will come. Okay, so now formal specification describes contracts with mathematical rigor. And why do we do that? We get a higher level of precision. We often understand better what is precisely what we are doing, avoid misunderstandings, avoid ambiguities. But the other very important motivation for this is whether you care for mathematical beauty or not, maybe you do care about automation of analysis. And there are different analysis techniques. One is runtime verification, which is what all this school is all about. The other is static verification, which is key tool is all about. There are also other things we can do on base of this, like test case generation. And so Nikolai will say more about, where's Nikolai? Ah, there, okay. Well, I guess you will say something about that. Test case generation? Yeah. Okay, so the general philosophy of JML is a tight integration of specification and implementation, for good and bad, right? I mean, this is a strength and a weakness we can discuss later, but this is the philosophy. So you have a single language, so you can view JML as an extension of Java. So JML is Java plus first-order logic plus all these contract structures, pre-post conditions, invariants, and more stuff. Annotations are attached to the program directly, and to ensure a compatibility with the Java standard, the annotations live in special comments, which are ignored by the Java compiler but understood by the JML tools. And here is such an example. So we now extend enter pin with specification, and I will go through the specification bit by bit. It's quite primitive for the time being, but I want to kind of introduce it from that corner here. Okay, so everything between this and that is obviously a Java comment, but in addition, if the Java comment is followed by this ampersand, then it is a JML comment for JML tools. So everything from here to here is a JML, is part of the JML. And then it doesn't matter if you write it like this here or you write it like that here. In both cases, JML tools understand that this is JML which comes. Then in addition, you see these funny blue things here, which are kind of used to further mark or highlight in your code the specification. They are not needed, but you can put them there, and they are ignored if they are the first thing which in a line. If the first thing in a JML comment in a line is this ampersand, it is ignored. So that's just a way to highlight these JML comments. Good. Now we see public here. This is specification, right? This specification is public. So we use the same visibility concepts, or almost the same visibility concepts in the specification as we use in the implementation. So this specification is accessible from specifications in other classes. And it can only mention public methods, public fields or public elements of this class. We are already violating that, but I will solve that later. Good. Normal behavior says something about what we need to guarantee in addition to what is written here. This here says that under this precondition, or under those two preconditions, this implementation is not allowed to throw any exception. Right? It's considered an error if these conditions appear, if these conditions are fulfilled, these preconditions are fulfilled when calling the method, and yet an exception is thrown. That would be an error. And this is what normal says. You are not allowed to throw any exception on the top level. You can use exceptions inside, absolutely, no worries, but you cannot, it has to be caught inside also. But you only, again, you only need you only guarantee this under those preconditions. Under different preconditions, there may be an exception, that's fine. Good, and now we have these two preconditions here, marked as requires, saying the customer is not authenticated, and the pin is the same as the pin of the card I'm pointing to, right? So this is a different object. This is a local variable pointing to a different object, and this is a field of that object. So not everything is totally local here. This is already going into a different class here. You also see that these conditions here are just Java Booleans, but that will change. We will generalize from that later on. Okay. So in general, in this example, it's Java Booleans, but in general, it's JML Boolean expressions, and I introduce them later. Good. So now a little bit of syntactic sugar. It doesn't matter if you write two preconditions or if you write one precondition with an and. That means exactly the same thing. Now the ensures, this is a post condition, which is guaranteed by the implementer of this here, given that at call time this here was fulfilled. So customer authenticated should be, so we just say ensures customer authenticated. That sounds a bit strange, but customer authenticated is a Boolean. So what we are saying here is that this Boolean must be true. So instead of saying customer authenticated equals true, you can just say customer authenticated. Good. Again, this is just Java. It could be more. Now you have seen one specification case. That was just the first part of my contract here. But there are other parts. Here is we had the correct pin, but we could have the incorrect pin. So we need to take care of other cases as well. So we have now two specification cases, and they are connected with this also. And here is then similar stuff. We are the biggest difference is that the pin is not equal to the correct pin in the preconditions. So now I'm pushing this up in the slide. So imagine the first specification case is written here. This is not JML syntax. This is just abbreviation on my slides. Now look at the post condition of this second specification case. It has this old function or functionality operator, this old operator. And what does it mean? So old, and then any expression inside here, it means E is evaluated in the pre-state, right? This is a post condition. So the entire post condition is evaluated in the post state, with the exception of what is surrounded by old. That is evaluated in the pre-state. So the wrong pin counter is the same as the old wrong pin counter plus 1. Yes? It is, so technically it rather means when you start execution of the method. Because the scope of the pre and post conditions is rather the local variables of the method. Otherwise you couldn't talk about internal things. But yeah, these things are fairly similar. But yes, the pre-state, that is when this execution started. Exactly. Yes? No. No. It just means that, so the specification language uses the same visibility. I mean, the general philosophy, again for good and bad, of a JML is to follow in very many conceptual things the implementation language. So they use the exact same visibility notions and the implementation. But what does it mean? It means this here is not Java. This is JML. So this is not a declaration of a Java variable or anything. This is just JML syntax. We are just here saying normal behavior. No exception shall be thrown here. And this specification case is visible by other specifications of other classes. So, or their verification. So when I verify another class which is using this one here, then you may incorporate in the verification of the caller. You may use this specification of the callee, and you can only do that if the specification is visible to you. Private specifications are used for kind of private methods, which where you also want a specification, but they don't matter for any callee. Yeah, good. Okay. And so this here, you can already imagine this is a challenge for runtime verification because we are mixing two states here in the evaluation. Then there is a third specification case. There's conceptually nothing new here, but the old is used in a more interesting manner, I would say. So if the customer is not authenticated yet, and the correct pin is the pin is not the correct pin, and the wrong pin count is too high, then what do? We do some kind of error handling if you want. The inserted card, the link to the inserted card is deleted, so we don't have access to it anymore from our implementation or for the next call. So if someone tries to do withdraw, will not be able to do that because it doesn't have any link left to the inserted card object. And we say locally, no, we tell that card that it is invalid. So we say that the inserted card, which was linked before, that the field, invalid field of that card has to be true. Right? You see here I'm mixing evaluation in the pre-state with evaluation in the post-state in one expression. Yes? That invalid is a field of the class which inserted card is the instance of. What's happening? Yeah. So inserted card is oh, this is terrible. I should not have done this. Okay, I regret deeply. Inserted card is a reference to a different object of type bank card, and that object has an invalid field. Now we go back. Can someone say something? I could sing in the meantime or something. Yeah. Right. Let me discuss this further. So please look at this. This is, Adrian would call it a quiz. Look at this quiz here. So if I say I ensure old inserted card dot invalid, or I ensure old inserted card dot invalid. Please, yes? Yeah, if you evaluate it at runtime, that could happen. Yeah, that's one way of putting it. Yeah, that's right. Other takes on this here? What's the difference in meaning? Let's say in meaning. Yes? Right. Exactly. So we have to talk about the old reference, because if we take the new reference, that would be null, right? So we have to talk about the old reference, but in the object which we referenced before, we now have a different invalid field, right? exactly. So that is the difference. And moreover, if you imagine such a thing being written in a post condition, and only using old, how could any implementer in the world do anything about the old value, right? You can I cannot, in my implementation, change the state in which I was called in, right? So it wouldn't make sense. Okay, good. But is the specification course complete? So we now said something about custom authenticated in this specification case, in the first one, but we didn't say anything about, in this specification case, about inserted card, custom authenticated. Oh well. No, this we say something about, but not about this and not about that. And the same holds for the other specification cases. We say something about one field, but not about other fields. And the intuition is, the other fields will not change. But that's not the formal semantics. So formally, we just say here that we change one thing, but we don't say anything about the other things, for now. And what you could do is that you add everything which has not changed and describe it in this way, that the new value is the old value. But that, of course, would be terribly ugly to add that everywhere. Your specification would be bloated by that. So instead of that, there is something like an assignable clause which restricts the locations you can, the implementer can touch and change. So an assignable clause like this here in JML, it says that no location other than those here can be assigned to in the implementation. Then there is syntactic sugar. We can say assignable nothing. Nothing can be changed, or everything can be changed. And now we can say, yes, custom authentic should be authenticated and nothing else should change. Or we do something with the wrong pin counter and we don't touch anything else. Or we change our inserted card and the invalid field of the inserted card, but nothing else. Yes? That's the specification, so that's an implementation issue. The specification only says what is true afterwards. This here, what should be true afterwards. Yeah, okay. It is you could not implement this here if you had no way of changing that. But whether you have public access to that field or whether there is a setter method in that class through which you could change it, all kinds of things are allowed. But obviously you have to have one way of changing this. Yes? Yes? And then change back. What do you mean? Yeah. So there are different semantic takes on that. Most things I have seen, maybe Nikolai, you can correct me or see how it is in other. But you would look at what you guarantee is that the value in the end of these things may be different, but of everything else may be the same. So you're not actually saying you don't write anything. You're saying, can it change or not? Can it be different in the end of the? So what you could do is that you write, you first write true to, you also write something to, let's say, custom authenticated. You switch it to true and back to false, and this would be fulfilled by most approaches, I think. If it doesn't terminate, it's allowed to do anything. But but you can say, and I have examples of that later. You can say whether it's allowed or not to terminate, and in which case it's allowed to not terminate. Yeah. Okay. Great. Good. So this is how you can also group assignables. So not only say this and that field is assignable, but I can say all fields of a certain object are assignable, or all elements of a certain array are assignable. Good. And now I come to more modifiers in JML. Spec public, pure, nullable, not null, helper. I start with spec public. So in our example, the preconditions and postconditions, they made heavy use of the class fields, but the class fields were private. So I broke the visibility of JML. So I have to fix that now. And there are different ways of doing that. The simplest one is so what you should absolutely not do is that you change your implementation, make everything public just to talk about it in the specification. That would be terrible. And instead, one way of doing is to say, okay, this is private from the implementation point of view, but public from the specification point of view, to make things visible, even if they are implementation-wise private. And that you can do by the keyword spec public. So in this bank card or wrong pin counter, custom authenticated, which are all private, I can make them spec public such that the public specification can talk about it. This is not the best way of doing it, but in a 1.5 hours lecture, the only way I have time to introduce, but I only want to mention that a more proper way to do that, which I would introduce if I had more time, is to have model fields. These are fields which only live in the specification world. They don't exist in the implementation world. They are public typically, and you define a relation between these public specification fields and your implementation. But I don't have time for that now. But you find it explained in our JML chapter here. No, this is not a nested comment. No, this is not a nested comment. These were the Java declarations. This is not these are the Java declarations, and I'm adding to the Java declaration this JML comment. Good. Purity is another thing. It can be very, very handy to use a certain, in a limited way, certain methods in the specification. For instance, to be able in the specification that two things equal each other, or that one element is contained in a list, or that the maximum element of this is smaller than the minimum element of that, or whatever. But if I want to use that in the specification, I have a problem potentially, because the implementations, they could change the state, and what would it even mean in the specification to use methods which change state. And so that is indeed forbidden. So there is a notion of purity. Pure is important, strictly pure is not so important now for this lecture. A method is pure if it always terminates and has no visible side effects on existing objects. Let's skip the strict purity for a moment. And so JML expressions, they may use pure methods, and I will have examples of that later, or here's one. So if you have a max method, which is a query basically, then you can use it. If you write pure here, this is a JML extension, then other JML expressions can use max, okay? But why are you allowed to do that? You of course have the obligation to show that it is actually pure, because otherwise you could just write pure, but it has to be pure. So it's an additional verification condition which you're putting here. Good. So pure is an obligation on the implementer. You can formally verify that something is pure, and yeah, okay. I think I move on. Good. Good. So far you have only seen Java booleans in JML expressions, not, and or. There are others like implication and equivalence. You can express them, you can compile them away, but it's quite nice to have those. But this is not enough. For instance, how would I express that an array only holds values smaller than 2? Or that a variable m holds the maximum entry of an array? Or this here is a kind of thing which you have when you have redundancy in a system and you want to specify that that you have a certain healthiness conditions in your redundancy, like all account objects which are stored in this array are stored as the index which corresponds to the field of that of that object. So basically, if an object knows where it's stored, so you have a kind of back reference, then that is a thing which you won't have to specify. But you know, we will not be able with Java Booleans to express these things. Any idea what we are lacking here? Quantifiers. Exactly. So this is actually a different example. Okay. Yes. So we need quantifiers. Java Boolean expressions, they extend Java, JML Boolean expressions, they extend Java by implication, equivalence, and quantification. So here comes the quantification. I can say for all x of type t, some JML Boolean, or there exists an x of type t, and here comes some JML Boolean. In addition, I have also these forms here, and they say for all x of type t satisfying a, b holds. Or there exists an x of type t which satisfies a and b holds. We don't need those things here for expressivity, but they are good pragmatically, and actually runtime assertion checkers heavily depend on those here. Let me talk more about them. So A here, if you use this here, it's kind of pragmatically used as a range predicate. It limits the range you're talking about. Oh, this is very sensitive too. Oh, sorry. Okay, these forms are redundant. I could express this here with an implication. I could express this with and. But why do we have them still? This here says, yeah, we are restricting this type further, and then we say something about that subset of the type. This is the pragmatics. For instance, an array is sorted at indices between 0 and 9. You would say for all integers ij, as long as these integers are in the range of my array, in the range I want to talk about, then the elements are sorted in a certain way. Or an array only holds values smaller than 2. Then I say for all integers in the range of the array, this is fulfilled. A variable only holds the maximum entry of an array. I could say for all integers, as long as the integers are in the array range, m is bigger or equal to array at I. And I is the variable we are quantifying over. Is this sufficient for a maximum? No? Because? Yeah, the main maximum may not exist here, right? We could say because this would be fulfilled if m was max int. Right? So it's not enough. We also need that there exists an index indeed where m is where we find m. Good. And here's another example which I talked about before, where I have some redundancy in my data. So here, for all integers in this array range, if I look in this array at position I, and then I look up the account number, I find I again. This is redundancy, and if you have redundancy in your data, this is an example of a healthiness condition which you then want to specify as an invariant in your data. Yes? Right, I mean, you could think of a specification language, JML doesn't feature that, but you could think of a specification language which says native, which has kind of native support for this kind of pattern, where you say, okay, for an array, for all indices of this array, right? So you have a different quantifier where kind of you have some operator which limits this quantifier to, yeah. So this here is just spelling it out in first order logic, but you're right, it could be done in a, this is a, yeah, actually there are many syntactic sugar things in JML, but not this one. Good. Yeah, and this here would be a kind of more drastic example. If I say all existing indices of bank card, they have different card numbers. I could say for all bank cards, this is not an array example, right? This is not array. Now I'm not quantifying over arrays. I just say for all bank card objects in my system, if the bank cards have different objects, then the card number is different. Right? This is the kind of thing which is very difficult, if not impossible, to runtime check. Because then you would, I mean, you can do it technically, but it would be, you would have to kind of have very good access to your heap and trace all the objects of a certain instances of a certain type in your heap and so on. Okay, good. Let me specify another thing which has a bit different characteristics where we use this first order stuff. We have a set of integers, and it's limited because it only has a certain capacity. This is the capacity, this is the array, it has a certain size. By size, I mean how much have we already stored in, in this set, how many elements do we have. So that's to be distinguished from the capacity. This is just a constructor, and now I have add, I have remove, I have contains and other methods. The first thing I do is I make these things back public to be able to talk about them in the specification. Again, in more advanced usage of JML, we can do other things distinguishing between the data you implement in and the data you see from the specification side. Not here. And then we make contains pure because contains is super handy to have in the specification, right? Not only we want to specify contains, but we want to specify other things with contains. Okay. And then in addition, we need if we specify non-void methods, we need access to the result value. And this is how we do it in JML. This keyword /result, it returns it refers in post conditions to the result value of the method. So I can say when I'm now specifying contains, I can say the result value, so it's a Boolean which tells me whether an element is contained or not. This Boolean is the same as this Boolean. There exists an integer in the right range such that the element is stored in that position of the array. Right? This is a specification of a return value, a Boolean return value, and this here is also a Boolean which uses first order logic to express the Boolean condition, right? So this is, here you see how we kind of mix Boolean types of Java with first order logic. Good. This is a specification of contains. And once you have this here, you can use that in the specification of your other methods without talking about this stuff here anymore. Because we already know. So for instance, in add, we can now say, okay, so if we still have space and the element is not yet contained, then the result is of add is true. You also have that in Java methods, that if I add something and it was not there before, you will have true as a result value. And the other things, you ensure that it is contained afterwards. And instead of saying there exists an index where I find it, I just say the method contains returns true afterwards, right? So after the execution of add finishes, if you then call contains, you will get true, right? This is a very nice way of structuring specifications where you can outsource these. So you have this stuff only once, and then we use it here, and we can only do that because contains was pure. Otherwise, the JML syntax checker will not allow that. Okay, what else do we ensure? So this is nice. This is not nice. It's very nice to say what we achieve, and it's often ugly to say what we don't achieve or don't want to achieve. So everything which was contained, everything which is not that element, whether it's contained before or afterwards, should be the same. Yeah. It's a more general warning. In this lecture, I use JML very extensively on all examples, right? So we try to express just everything with JML. In a practical example, you would not do that, because you don't want the specification to be a lot more extensive than the implementation. So in practical examples, this is not typical. You would maybe not say this here in a specification, and then your specification is less complete. There's always this trade-off. Good. Then there's another specification case if the element is already contained, or we have reached the limit, then we return false and yeah, something. So nothing conceptually new here. If I remove something, then the most important bit is up here. We guarantee that afterwards it's not contained anymore, right? And this again, this thing that we don't change anything else. And here we say how the size is affected by it being contained afterwards or before. So if it was contained before, then we have to decrease the size, otherwise it stays the same. Again, you see, this is a very, very complete style, which is not what you do in practice all the time. Good. So far we have used JML to specify methods, but how do we specify constraints on class data? Like consistency of redundant data representations. This is a very important problem for verification. Imagine you have a database of books, and the titles are stored in the books, but then you have also some indexing of the words in the titles in some other indexing list which refers back to your books, and I don't know, if you have such redundancy, you have to specify it because it so easily breaks in the implementation. Another example is restrictions for efficiency, like sortedness. I will have an example of that. So data constraints are global to the methods. And let me extend my integer set to a sorted integer set now, where we say that this array is sorted all the time. And how can we express that? Oh, why? Let me jump over this. Yeah. How do we specify sortedness? We can. We already had that. I can say for all integers in the right range, the array at I-1 is smaller or equal to the array at I. What happens if size is smaller than 2? If it's smaller than 2, then there is no I between 0 and size. Right? But what's the meaning of this first order expression if there is no I satisfying this condition? True, exactly. It's trivially true, and this is very important. Good. So now we have to assume sortedness in the pre-state and guarantee it afterwards. So for instance, this contains method, it has to assume that because the implementer of contains will rely on the sortedness. And we could do that by spelling it out in a requires, but that is not enough. Then we also have the remove, and then we would have to require and ensure it because you remove in a certain way when some things are sorted, but you have to kind of keep the sortedness. You in add, you have to again assume it because you will only look until so and so far if things are sorted, and then you know exactly where to add. But you have to do that in a way such that sortedness is kept, and so on and so forth. So, and this becomes ugly if you add that just everywhere. Here again. So instead of that, we use JML class invariants. So all these blue parts from this. All these blue things here will be deleted now, and instead I formulate an invariant here on the data in this class, which says exactly that this array here is sorted, and that is an invariant. And with that, this becomes an implicit assumption on all methods and an implicit, so it kind of, you can imagine it being implicitly present in all requires and or added to requires and added to all ensures without spelling it out. Good, you can place it anywhere, but it's custom to place it kind of syntactically close to the fields it talks about. Yes? No, that's right. This is not loop invariance. I will have one slide about loop invariance later. So the loop invariant is rather a help for the verification, not so much specification. This is an invariant on the data which should hold at specific points in the computation. In particular, you assume it when every implementer assumes it and ensures it. So it will, as long as well, maybe I have here. So class invariants, they must be established by constructors and by static initialization. And then they must be preserved by all non-helper methods. I come to helper later. So you assume them in the pre-state and you ensure them in the post-state. Yes, but thank you. It's not has nothing to do with loop invariance. In particular, they can be violated during the method execution. So they may be violated even by a loop, but not when you finish execution of a method. Okay. Yeah, this is not good. But there is an exception to that. We can specify certain methods as helper, and then we do not use this assumption that invariants need to be preserved by those helper methods. So a helper method neither assumes nor assures an invariant by default. And what is the pragmatics of that? Helper methods are usually private. They are used for structuring the implementation of the public methods, and they can be used in constructors also. And an additional purpose, which I have slides on later on, when we generate logic from the specification, we can kind of normalize JML, and then helper also plays a role. See about that. Good. We can also explicitly refer to invariants of this or of other classes. So there is this construct invariant for O as a Boolean Java expression, and it is true in a state where all invariants of the class of O are fulfilled. How do we use it? We can use invariant for this when we want to state the local invariant, but it's not implicitly there, like in helper methods. Or we use invariant for O, where O is a different object, in order to require or ensure the invariant in a local context. So if I want to talk you saw this example where I talk about the invalid field of a different class. So if I want to say something about the invariant of that class, I can do that by saying invariant for O or for bank card or something. Yes? Not in JML, but there are extensions, or they are more on the program logic side, I would say. So this here translates, this specification language translates to program logics, and there, like in the specification, you say something about specific points and not about the duration. But there are extensions in program logics which do that, which allow you to talk about during the execution of this here, something is not is fulfilled all the time. But it's kind of it's not. I wouldn't say it's mainstream work, but there is some work which bridges this gap which we have between temporal approaches and those approaches where the temporal approaches talk about the duration, maybe infinite duration, or maybe about an interval, and here you talk about specific discrete points, and in between you don't know. So, for instance, for certain safety properties, where certain things should never, a red light should never become, no two traffic lights should be green at the same time. It would be very difficult specify that here because you don't have control of what happens inside the method. Yeah. So the short answer is no, but. Okay. When do I may use this invariant explicitly at the local invariant? You saw like this here, invariant for. Oh, where is it? Invariant for this. I show you a use case for that now. So imagine I have some database implementation here. I have a method add, which adds a whole set of items to my database, and then in a kind of rough and ugly way first, and then I clean up. For instance, maybe you have some sorting, you have some trees here, which you first add it anywhere in the tree, and then you sort the tree, or something like that. This clean up should then better be a helper method because it cannot assume that you left everything clean and nicely. Actually, its purpose is to clean up things, so it cannot assume clean data. So it will become a helper method. So it doesn't assume the invariant, but it should ensure it, because that's the purpose of this cleanup. Right? This is just an example where you want to spell things out. Because as soon as I have helper, I have no implicitly given assumptions or guarantees about the invariant. Good. And then the other example is not to talk about the invariant of me, but the invariant about someone else. And in my bank card example, which I had before, I could, for instance, say that my invariant in my class, or in the ATM class, is that if the inserted card reference is not null, then the invariant of the inserted card should hold, whatever that invariant is. It's specified elsewhere. Good. Yeah, I think I skipped this. And static and public. Okay. Now recall this enter pin thing here. All these three specification cases, they talked about normal behavior. In particular, exceptions are forbidden. But we want to sometimes work with exceptions. And we even want to throw exceptions by some method, and other methods will catch them. So we have to do more. Normal behavior, in a normal behavior case, it forbids that an exception is thrown. And an exceptional behavior case, it requires that an exception is thrown. The keyword signals, it tells me what should be true after the exception is thrown. So you throw an exception, but you have left your state in a certain way, and maybe I want to say something about how you left your state. And I can do that in the signal clause. I will show that to you. I can say which exception should be thrown. And here is a specification case, an exceptional one. If, for instance, I call enter pin, but the inserted card is null, then an exception should be thrown. So this here says, I must throw an exception as an implementer. This here says, and the exception which you throw has to be of this type. And this says, if an exception is thrown of this type, then this here holds after throwing the exception. So the customer should not be authenticated, right? Yeah, and this is just saying what I just said. And more generally, I can have a whole list of exception types which I allow here, and this is the general syntax. If this exception is thrown, then this is a post condition. I'm very unhappy about this signals keyword because, yeah, it specifies a post condition under a certain exception, but I cannot change that. Good. Now we come to termination. Someone asked about that. Both the normal and exceptional behavior by default require termination. Maybe exceptional termination, but termination. But you can override this default. You can, to specific specification cases, you can add this here, diverge is true. And that means in this specification case, I allow non-termination. For instance, you could say, okay, this is a square root algorithm, and there's a front end at the GUI side which kind of makes sure that negative numbers never reach the call. But then the implementer of the basic square root algorithm can assume that or only needs to terminate in the good cases when it gets positive numbers, and it's allowed to non-terminate when you get negative numbers, as an example. I don't think it's a good example. Maybe division by 0 would be better. Okay, so this here means that given the precondition of this specification case where this appears, the method may or may not terminate. You can do more fine grained than that. You can even have a Boolean here, a Boolean which says this, for instance, diverges x greater or equal to 0. Diverges x smaller than 0. Then you say I allow non-termination if x is smaller than 0. But I don't see so much use of it. I see most of the time this year. Okay, then another discussion point is null. Null is a constant headache to everyone who works with specifications. Class fields, method parameters, returns, they may or may not be null. And they can be declared we can allow null or disavow null. For instance, we can say that this field here should never be null. So if you write this here, then implicitly you get that. You can say that as a precondition, this is a kind of implicit precondition that this is only called with a non-null thing. So if someone calls me with null, it's a caller's problem, not mine. This is a precondition. Now, this is a postcondition if you want. This says that the return string will not be null. And it can all be compiled away into ensures, requires, or invariant, but you don't need to do that. Non-null is the default, so you don't even need to write these things here because non-null is the default. So if you don't write anything, then we have non-null. So, and this is actually a problem sometimes, that people are not aware that if they don't write anything, they forbid null. So if you don't write anything, like on this slide, then the invariant says that this name should never be null, or this should not be called with null, and this should not return null, and so on. I think it's a highly problematic design decision to have such a default. And it was not like that when JML started, but yeah. But you can allow null, and that you have to do then explicitly. You have to say nullable, nullable, nullable if you want to allow null. Let's look at this here. This is a linked list, very primitive. We have an object which we store there, and we have a next field. So if I don't write anything more, and I use this in a JML context, what does it mean? Yes? Yeah, so the default applies. So null is forbidden here and null is forbidden there. What does that mean if null is forbidden here? Well, it works, but then all linked lists have to be cyclic, right? Because you should never reach null, right? And this is not what you want from a linked list, that it has to be cyclic. Rather, it should not be. So this is yeah. So instead, we would have to write this here in a verification context. Good. So the general, you saw exceptional and normal specification case, but the general case is a generalization from that. It's just as behavior, not normal, not exceptional, just behavior. Has requires, diverges clause, assignable, ensures, signals only, and signal, and some more, which I don't discuss in this lecture. And here's then the kind of semi-precise meaning. An implementation of a method M satisfying this behavior specification case has to ensure the following. If property P the precondition, holds in the method's pre-state, then one of the following must hold. Either D holds, in which case we are allowed to not terminate. So D holds and the method does not terminate. Oh, actually, I think I should write here, if D holds, then it's, oh, let me see. Yeah, okay, no, it's correct. Either D holds and the method does not terminate. Or in the reached prose state, normal or prose state, all of the following items must hold, all of them. Only heap locations which are specified in the assignable clause have been changed. And by be changed mean they are unequal to what we had in the beginning. If it terminates normally, then the post-state property has to hold. If it terminates abruptly with an exception listed in the signals only, then it's terminated with such an exception. And by the way, runtime exception and error are also allowed, but let's not think about that. And for the matching signals clause, the exception postcondition holds. So this is the semantic of a general behavior case. And in addition, invariant of this must be maintained for all non-helper methods. So if it's a non-helper method, then we will assume and guarantee the invariant for this. Good. Now I talk a bit about desugaring. Briefly. So a lot of things are not necessary in the language and could be compiled away. And I discussed that briefly for two reasons. One is that you get some semantic clarification. And the other is this is kind of the pre-processing step for static verification and in some sense also for the runtime assertion checking tools. So if you have a normal behavior case, that desugars to signals false, because signals false that if any exception is thrown, this postcondition should be true, which it never is, so no exception can be thrown. Right? So the exceptional behavior case desugars to ensures false, because after normal termination, false should be true, which it never is. Okay. Then, sorry, I talk about the normalization later. I want to have a word on ghost variables. Ghost variables are specification-only variables which are preceded by the keyword ghost. They are updated by a set annotation, and they can be local fields or local variables or fields. And the typical usage is that you, for instance, you mimic a state machine in JML, then you have these specification-only fields which are the different states, and you tell how the machine moves in those states. Or you want to store and express some additional information, like for instance memory usage, execution time, and stuff. This here would be an example of a ghost variable which counts loop iterations here. I set it to 0 here, and I increase here. It's very operational, right? Here we have ghost variables for memory usage, and I can, whenever I allocate something, I can set this in a new way and so on. Very operational. A less operational way of doing things like that is model fields, which I don't cover here. Okay, static verification of JML. One of the tools, and I think it's, yes? Please. I can do that, absolutely. I have 10 more minutes or 15 more minutes. So, yeah, we could 2 minutes break, and then I have 15 minutes left. I'm very positive there. I think my lecture is 1.5 hours. Should I move on? You thought it was 2 hours? Yeah. No. Okay. Static verification of JML with the key tool. So I think it's fair to say that key is the state-of-the-art tool for doing verification of JML. or doing verification of object-oriented source code altogether. The key is an approach and tool for form specification and inductive verification of object-oriented software. It's done by these places, at these places by these people. This is me here with Karlsruhe and Darmstadt on board. In 30 seconds, it uses a certain program logic. Program logic is the most famous example of that is Hall logic, but we use a different one. We use dynamic logic. The verification is based on symbolic execution. So the calculus, when the proofs evolve, these proofs, they symbolically execute the program, and they kind of compute the substitutions which the program then does on the formulas. Symbolic execution plus induction or invariance for looping stuff or for recursion. The calculus is a sequent calculus. The prover is designed as an automatic prover, but today is used mostly in an automated fashion. Automation is very high. If you get things like loop invariance right and so on. So Java is a target language, and we support JML as a specification language. And the major components of Key is a proof obligation generator, which takes Java files and JML files and then generates formulas in that logic. And the key prover, which proves this thing dynamic logic. I will not say much about it, but it is actually quite related to the logic which Adrian talked about this morning. If you in the modalities would not just have actions but full Java programs, then you have dynamic logic. The key prover then is a prover for that, but we also have some other things include. I will only mention one. The key test gen is a test case generation tool based on verification. So we build proofs without trying to prove anything, just using the symbolic execution, which we can see in the proofs, and then we can read from the proofs branch conditions for which we generate tests, and we get a very high coverage criteria for that. Okay, I cannot go as far as introducing this translation to you, but I want to, on the JML level, I want to say something. So this JML is normalized first into normalized JML, and then we generate something in our program logic, which says here, given a certain precondition. Here you see the modality from Adrian's talk, but here inside we have a call to method, and afterwards the post condition should hold and some framing conditions. But let's not go there. Normalization, I just give a flavor of that. If I have a normal behavior, so the idea for the whole normalization is to get rid of defaults and make them explicit. And get rid of syntactic sugar. So instead of normal behavior, we just write behavior, but we say signals false, no exceptions allowed. Instead of let me see, what is this here? Yeah, then the nullable non-null defaults are added. So we write nullable even if it's not nullable, but we write it and then make explicit that we don't allow it. So we make everything explicit on the logic side instead of in keywords. We want to have everything in logic in the end of the day. We make the invariants explicit and so on. We make everything helper because that is most permissive, and then if it was not helper, then we would have invariants everywhere, and so on. And then in the end of the day, we translate from this contract, which says the that the post condition, it states that either no exception is thrown, or in case the exception is thrown, the exception post condition has to hold. So we have to take care of that in our logic. So now in this modality here, this black part in the modality, this is Java, but the thing we want to verify is just this little m here. This is the code we want to verify. But now in order to be able to talk about exceptions being thrown by this m and result values, which it returns, we first assign it to result, and then we do some try-catch around such that here in the post condition, we are able to talk about the exceptions which are thrown because they are caught again, right? And you do things like that. This is just to give you some flavor where we're using Java to express that we catch exceptions and then talk about them. And in runtime assertion checking, you do similar tricks. Gerardo has been asking this question. In JML, you have also loop invariants. And loop invariants, most people say this is also specification. I say it's not specification. This is for provability, you give annotations to the code which tell you what the prover, for instance, which loop invariant a prover should try when coming to this point. But let's now finally move to runtime assertion checking of JML. This school is about runtime verification. And openJML is the tool which should be used for that. It also offers other things, but in particular, runtime assertion checking is, I think, what it's particularly good for. It also offers some lightweight static verification, and David Cook is behind it. So what does a runtime verification tool have to do? It has to address certain concerns. Operationalization of quantifiers, that's a big concern. You have to deal with these old expressions. You remember we had a post condition which mixed talking about, which related a post state to a pre-state. So you have to be able to operationalize that. You have to do something about these specification-only things. Ghost variables is not so difficult. It turns it into normal variables and just computes with them. Model variables are a lot more difficult because they are specified in a declarative way, like specifying a refinement relation between your implementation and the model variables. That is much more difficult to runtime verify, but it's possible. Methods can have multiple exit points. That can be a problem for code instrumentation. How do we even talk about how do we check exceptional post conditions? And actually the trick here is similar to what I showed you in Key, that you have a try-catch around and then you catch an exception and talk about it. Undefinedness and so on and so forth. This is what you want from a runtime assertion checker. It should be transparent. So if no assertion is violated, then the runtime assertion checker does not change the functional behavior of the system. The efficiency of the system, of course, is very, very much affected, but it should not change the functional behavior. Annotations should tell you where they occurred. The tools are not very good on telling you why it occurred, but they say at least where exactly, both on the caller and the callee side. And only real violations are reported. That relates to the soundness, which Adrian was talking about. And then it's also desired that you minimize runtime overhead, but runtime assertion checkers are not good in that. It's not that the tools, actually it's a bit unfair because the specification language is so powerful. It can quantify over all instances of bank cards or what, and then you have to instrument your code to find them and check something everywhere. And that is, if you use it in just arbitrary ways, it will slow down your system in an unacceptable way. So a more typical runtime assertion checking usage is, okay, you have a special command compilation option, code instrumentation on the bytecode level, it inserts checks there. Execution with runtime checks are enabled in the debugging phase, but they are often not enabled in the deployment phase. And this slide tells you that we can have debates, good debates about whether you even should call this runtime assertion checking runtime verification, because it's so prohibitive on the execution side, time side. This is an example of an output where openJML finds a problem, and it will signal the problem both on the callee and the caller side. Okay. Now I wrap up. The Java modeling language is a specification language. It talks about data properties at specific code positions. It combines Java object-oriented concept with first-order logic. It's used for static verification with, for instance, the key tool. runtime assertion checking in openJML, but also for other things. For instance, on this slide here, this problem which runtime assertion checking has with the performance, the runtime performance, can be addressed by combining static and runtime verification. And I think Nikolai will say a lot more than I do about different combinations and using different techniques, dynamic, static, combined in different ways to reason about dynamically and statically about specification languages of this style. We also made a contribution here, I think, in the Star Wars approach, which uses not only JML, but it builds also on JML. And we try to prove things statically as much as we can with a key tool. Then we look at we analyze these failed proofs. Most of the time they fail because we use them in a primitive way and without user interaction. It's not PhD students using it, but just in an automated fashion. And then the automated analysis of these proofs tells us, okay, this part of the proof is closed. So if in all executions which would fit to this path, we don't need to check at runtime. But in this path, we need to check at runtime. So we generate path conditions under which you need or not need to verify or check assertions at runtime. That's the key thing there. A similar technique is used in test case generation, where you also you generate failed proofs and then you generate path conditions under which you come into these different parts of the proof, and then you get high coverage. JML unit is a tool which is used for that. You can do it in key test gen. And for other languages than JML, other tools are there, and Nikolai will elaborate on that. Some credits. So my slides here are all mine, with this exceptions here. The runtime assertion checking part and the ghost variable part is based on material by Marike, and Marike and myself and two other people, we have written this Java modeling language tutorial, so it's only natural that we kind of combine this our material. And that is what I had to say. Thank you very much.